Hello, ladies and gentlemen. It's time to start to talk about our case study and our basic and initial problem. So first of all, let's focus on this at the beginning of the video, that what should we solve, and then what kind of company do we talk about, which tries to provide services to solve this issue. And then we can start to focus on corporate specific issues, so not just industry specific issues. So if you are looking on the sample industry, which is orbital launch business, especially commercial launch business, then this is what we have to solve. So if we are living here on Earth, then there are different orbits where we can launch satellites mainly. So we can launch things to low Earth orbit, sun-synchronous orbit, and geostationary orbit. Once we are able to reach 160 kilometers altitude, then sooner or later we are in space, so actually above 100. There is space, but still drag of the residual atmosphere can be an issue. So if you would like to maintain orbit, then 160 is important. So from economics point of view, doesn't matter. So we need a rocket to do that. After that, this is just an engineering problem. So what kind of altitude do we want to go there? If we have a medium-sized rocket, it doesn't matter. It will have enough energy and we can move enough mass. And if we are looking on the order types, then we can find mainly satellites. So it can be for communication, it can be for observation, navigation, astronomical, and so on. So we can have a communication satellite to provide internet, to provide TV, or any kind of data relay. Earth observation satellite can provide data about like Google Maps, for example, or Google Earth, where we can see how the Earth looks like, or it can provide data about crop diseases, soil moisture, weather data, and for navigation satellites, for example, GPS analogues, so global navigation satellite systems like GPS, like GLONASS, like Galileo in Europe. We can find many different applications, and also astronomical satellites, which can be used for science. So it can both look at Earth, or it can look outwards towards space. Yeah, so this is our main market here. We have also the International Space Station, also on low Earth orbit, so they are usually around somewhere between 300 and 500 kilometers. But their service is a different market. So right now we are just focusing on this conventional thing. So our company in question is ArianeSpace, which is a French company, and practically they are focusing on communication, navigation, and science and Earth observation satellites, and also technology demonstrations when they are checking a new engine, a new sensor, anything like this. And in the past, they had Ariane 5 launch vehicle, which is now retired. They had the Soyuz because they purchased these rockets from Russia. But due to the sanctions now, they are not able to do that. And there is the lightweight Vega, which we ignore in the case study because, unfortunately, this rocket has a really terrible reliability. So during the recent decade, many of their launches were unsuccessful because of explosions here and there, or no lack of ignition. So yeah, let's ignore this. Let's focus on the main vehicle, because Ariane 5 will be changed now there will be a new rocket called ArianeSpace. So this is the new launch vehicle. We have quite a distant photo, but doesn't matter. So what matters for us, because we are still economists, not rocket scientists, that this project is in a huge, enormous delay. So as you can see here on Wikipedia, then they were expecting 2020 as the deadline for the first flight, and right now we are in 2024, and yeah, first test happened in April. So practically right now we can see that the first core stage, so the middle part of the middle section of the rocket, and the boosters, which are on the sides, were transported to French Guiana, because in French Guiana this is where the launch is happening. So we have one launch site near at the equator, so that's why we have highest efficiency. And so from financial point of view, this is one issue, that there was a huge delay. So that's why companies and even the European Space Agency, which contains many European and countries and also Canada, moved some of their launches already from Ariane 6 to SpaceX. And this is the second problem, because we are absolutely not cost competitive. So cost per launch is somewhere between 75 to 125 million euros, which is terrible. So right now, if we are going to SpaceX, we can have services for, in average, 67 million for a Falcon 9 rocket. And obviously this number is bigger, so yeah, we are not cost competitive. Then your question can be, but how deep is this market? So if we are checking value chains in the Refinitiv Icon database, then we can see sooner or later, once it's loading in, that ArianeSpace business partners are not just reduced to European companies, because, okay, there are Eutelsat, which is a French one, SES is from Luxembourg, Viasat is from the US, JSAT is a Japanese company, there is one from Germany, Malaysia, another one from Luxembourg, Brazil, Italy. So we can see that this launch platform is designated to serve global markets. So it's not just for European companies. So what happens if we are more expensive? Obviously we will lose launches. So if we are checking right now the books, so what kind of orders do we have here for Ariane? Right now it doesn't matter that it's 62 or 64. The second number is that how many solid boosters are attached to the vehicle. So in this case, we can see that this is not much. Absolutely not much, because, yeah, so we have 2 for this year, 9 for the next year, 4 for after that, 2 and 1 later on. The problem is that we are not able to scale up. So at the same time, for manufacturing purposes, we have to build this vehicle. So practically we have to build engine, we have to build the whole hull of the rocket, so the tanks inside. So we need hydrogen tank, we need an liquid oxygen tank, Also within the second stage to move cargo up, because usually first stages are just operating for 100 or 90 kilometers or something like this, and then second stage is bringing stuff to orbit. So we have to manufacture all of these things, so we have to have at least several 3D printers, several CNC machines, and other really expensive manufacturing machinery, and we have to maintain it. So if we are just operating on a small scale, then practically we are not able to reach any economics of scale. So this is the third problem, that low launch cadence is terrible for profitability. Okay, so you can ask the question, but okay, how SpaceX can maintain such low prices? And the reason is because Falcon 9 is special. So, first of all, if we are checking the data, what we cannot see here is any solid rocket booster. Because one solid rocket booster, you are not able to recover it. It's not refurbishable. You are just shooting up 8 million euros per pieces, and after that it's not coming back. Or it falls back into the ocean, but you are not able to refurbish it. So that's one thing. Second thing, that the first stage represents roughly 75% of overall manufacturing cost of the rocket. Because the engines are the most expensive component, but still there is the aluminum or sometimes carbon composite rocket body, and also there is an engine, usually one engine only in the second stage, and there is also some plumbing and tanks for the second stage as well to provide oxidizer and fuel for the engine. And then here under the fairing, then we have find our satellites. So this is around 25% of all the costs. The fairing itself is usually around 7 million euros or US dollars. So if we are able to recover the first stage, then we can not just recover, but able to reuse immediately without taking everything to pieces. Then we can have cheaper prices. And this is what SpaceX was able to solve. So they can land this first stage propulsively. So it means that they are launching stuff into space. And then they are, once they ejected the second stage, then they can land. Yeah, so they can land on land, or they can propulsively land on sea. So they have this nice foods for feet, and yeah, this is the. So once they are launching, then they are separating the second stage, and after that there is a reignition. It slows itself down to get back from orbit, and once they are near the barge or at the sea or at the landing site, depends on the mass of and also the orbit of the satellite, then they can land propulsively, and after that you just have to check the injectors. You have to remove all the nasty components which were just a result of burning the engine, because it burns kerosene, so it's not that clean. And but once you clear the injector heads, then you can reuse the rocket. So they were working on it a lot, but and at the first years we were able to see really nice explosions, but nowadays this is quite a routine. So we can see that launch and recovery numbers are really high. So if we are going back to the first page, then we can see yeah. So you can see that its launch success ratio and recover success ratio is 98% with the current version. So they were running different blocks, but the final version was block 5, which was fine-tuned for such purposes. So this is how we can reduce costs efficiently, because after the first stage survives the first launch, then practically your manufacturing costs are reduced to just fueling. Fueling is marginal, so we are talking about several hundred thousands of euros, while we are talking about 10 of millions in terms of rocket manufacturing. So fuel doesn't matter. And also, if we can reuse 10 times the first stage, then already we can cut prices a lot. So this is how market was able to move, orbital launch market was able to move from the more than 100 million US dollars or euros to the 70 range, because above this you are not cost competitive at all. Yeah. Okay, so that was our initial problem. So let's see how can we have the design. So I prepared many different engines for you, because in this case we can choose, but first let's build up our own or the original rocket. So ArianeSpace will still use the old Vulcan engine, just they updated it to Vulcan 2.1. So this is how the original engine looked like. So we have the engine nozzle. This is where the hydrogen and the oxygen is mixed together, and then through engineering stuff, then it starts to burn here, and after that the rocket moves upwards. So from economics point of view, this is what matters. And the second thing is that how fast and easily can we produce this. So that's the difference between the second version or the newest version of the engine, because as you can see, they were able to cut back many of the components. So, and many pieces which were manufactured by hand in the past because you needed precision, nowadays you can 3D print. You don't have to put manually small pieces together or weld them or and so on to connect them, because nowadays you can print it up. And it's not just faster and more reliable, but also you can sometimes save 1/3 of the materials, which can be really important if you are manufacturing things, for example, from titanium. So that's why it can be really important. So let's use Vulcan engine. Otherwise, you can select Merlin 1D, which is operating Falcon 9. Also, I provided data about pricing. So what is the price of this thing? Obviously, they are mass producing this Merlin 1D at SpaceX. So hypothetically, if you are able to buy these, then this can be quite cheap. But also at the same time, we need a lot of them. So Falcon 9 is the name of the rocket, and obviously 9 engines are required to run the first stage, and 1 additional for the second stage. Also, it requires a lot of fuel in tonnage. It's kerosene fuel. And also what is important here, that kerosene is really good because you can store it at room temperature. You don't have to keep it at low temperature like hydrogen. Hydrogen, you have to go nearly to absolute zero to liquefy it efficiently and to store as much mass in the same volume as possible. So these cooling expenditures are not present in case of kerosene. And obviously we need oxidizer, but all of these engines are requiring here liquid oxygen, and you can generate liquid oxygen by using electricity. So that's why it's not a cost factor here. So we can liquefy it from air, so it doesn't matter. What matters the fuel here. And also you can see here some reliability, because it's a really nice thing to launch stuff into space, just sometimes mishaps can happen. So if we are looking, for example, on Antares rocket, which was developed by Orbital Sciences, now it's part of Northrop Grumman. Practically what they did here, that they imported engines from Russia, they imported the first stage and mostly of the tanks from Ukraine, and they were just integrating things together. And the problem was that if your engines are corroded or not tested enough, or because rockets are the first 20 launches, they are not reliable completely, then well, this is what can happen. So yeah, after that NASA asked Orbital ATK to test more their engines, and they switched to another Russian engine. So yeah, that was a sad story. So that's why we have to be careful, and also that's why we have to be accounting reliability of the launches. So you can see here launch success to failure ratio for each rocket, how many times they were launching. In this case, BA4 engine is quite misleading, because they had only one demo launch in this year, finally, with the Vulcan Centaur rocket. So, because Blue Origin sold this engine to United Launch Alliance for their Vulcan rocket, which means that, yeah, right now they have 100% efficiency rate, but I set it to the more conservative 3%, let's say, because that was just one launch. Because you can see that once they are able to launch things in higher numbers, then sooner or later mistakes are found here and there, and then it will be reliable. So also most of the engine problems in case of Ariane 5 or in case of Vulcan happened at the first years of the launch vehicle, and after that, once it became mature, then it was no problem. So we have reliability. Can it land propulsively? Right now we can say that the design is not allowing it, but we are not engineers, we are economists, so let's assume that okay, we can do this. Also, I removed solid rocket boosters from the Excel sheet because it would just complicate stuff. If we needed solid rocket boosters, then I just added one additional engine, because yeah, if you need solid rocket boosters, it means that your engines are insufficient. So if we are increasing their numbers, then this will be managed by economics. Okay, but there is an additional thing. So if we have to make them recoverable, so first stage must be landed to have partial reusability, partial fast usability, then they need to have a learning curve. So at the first years, they will explode miserably. So 67%, 44%, 7%, and so on. Once we can reach this nice 9%. Practically this data is coming completely from SpaceX because nobody was able to achieve this yet. Blue Origin wants to do this, but their New Glenn rocket will be also partially reusable, will be expected to launch only in this year's September. So that's why we have no data. So this is what we can have. Okay. And you can ask the question, landing propulsively, what do we need? We need to be able to decelerate, so we have to be able to regulate the engine. How many power are they providing? So not just running 100% like a solid rocket motor, but throttling down nearly to 30%. If you can do this, then you can land with this one. But right now we can say that we can do this, so we don't have to think about. And also, if you would like to have some new fancy engines, we can select Raptor 2, which is also developed by SpaceX, and now they start to fly this on their Starship project, so we can have some data because, yeah, and the first launch, orbital launch, only 23 survived until the vehicle exploded. Then at the second launch, all 33 survived. And at the last third launch, also 33 survived, and this thing nearly landed, just it failed to ignite, so it exploded half kilometer above the ocean when they tried to land this. So we can say that now the engine has some kind of a reliability because now all of them are igniting and they are not exploding during this 10 minutes of operational time. So we can say that, okay, 10% of reliability we can plan with these vehicles. And also methane is really useful because it's not as polluting as kerosene. I mean polluting for the engine. So you don't have to clean the engines so much. That's why you can reuse it practically immediately. So methane is like gas, heating gas, natural gas, that you can use in your oven. Just it's more cleaner and it's also liquefied to put as much mass in the storage tank as possible. So yeah, there's all the things to know. So let's use this one. I will apply a nice yellow color. So we need the product. How many engines do we need? Okay, we need the name of the engine, so let's copy. We have Vulcan. We can select that we can use different engines, but come on, let's keep things simple. How much do we need? Okay, we need 2 here, 1 here. And what is the price? Okay. Then fuel type. Fuel type will be hydrogen. Okay. We can manufacture the hull or body, rocket body from aluminum or carbon composites if you are checking the data. So this is the rocket body for economists, both for the first stage and for the second stage as well. But no, I updated all these databases, so that's why you can use the Excel. So rocket body, it can be manufactured from carbon composite because it's lighter than aluminum, but it's way more expensive. So you can do this if you would like to build the Ferrari for the rockets, but nowadays only Firefly and Rocket Lab uses carbon composites. All the rest of the market is using an aluminum lithium alloy. Okay, and yeah. So total fuel, name hydrogen, and we need also the mass. 24. Yeah, it's obviously lighter because it's hydrogen, so the lightest element in the universe. So we have to put here the amount. And then let's check for prices. So we have to keep everything at minus 53 Celsius at a really high pressure. Otherwise it blows off, so it expands and rocket goes boom. And it's quite expensive, and the problem is that also hydrogen is absolutely corrosive. Yeah. And it's also it's really hard to seal down, so that's the reason why usually nobody uses hydrogen anymore, just NASA and ArianeSpace, which is great. Okay, so aluminum. Then we have to define prices. So obviously first stage what we can recover, so we have 2 engine multiplied by the price, plus we have the body and the price, and then we can recover 30 million euros. But obviously we are not able to recover the second stage, so 1 engine will be lost anyway. Oh, sorry, that's a multiplication, and plus we have, oh, it's already done. Okay, then we don't have to multiply the second thing. But we still need to multiply this stuff and also the fairing. Okay, SpaceX yes, recovers the fairing as well, but this euros per tons. So practically this is 0.006. In this case I don't have to deal with that one. So these are the costs, and actual price tag is more reasonable. Yeah, so these are the costs. So the actual price tag can be promisingly low if we are able to recover this. You can say that even without recovery, why we are so expensive here. The prices, yes. Okay, it's because I mismanaged. Okay, let's check it again. Okay. So if we can use this N9, so the total price of the vehicle plus G5 must be manufactured 9 times, then practically we can say that, oh, we can operate this quite smoothly and easily. And I set 20% margin. So we are easily here, but obviously we have these ranges. So if we are under 60 million euros, then we can have boost or premium in pricing, but we are under, so let's raise it, because we are not stupid, we have to have profit maximization as much as possible. Yeah. So now we are still under 60, but we have nice margin as well. So half of the rocket. So that was the first problem, to design the vehicle. Okay, then now we have to integrate all these things. First we need RUD, probability engine. Rapid unscheduled disassembly. So engine goes boom, and that's why rocket goes boom boom. Probabilities, so we have to just pick this number. Here in the first year, and after that we just have to check what is happening. Yes. Okay, there are no further instructions about this, so we have to let's keep it the same. Now we can keep it the same, and also stage, because all the plumbings and hardware must stay at the same place, because Falcon 9 had an early version of Falcon 9 had a stage collapse issue when they were launching it, and at some height and some load, the first stage, for some part of the first stage, completely collapsed because it was not able to keep this or meet this dynamic pressure. So we can learn a lot of things during the first years, but after that all these plumbing issues will be solved. So we can see that the rocket will be quite reliable already. Okay, first stage landing probability. So we have to set it as well. And then we have these numbers. So let's copy them. Number, transpose. Yep. Okay, this is a percentage number, and after that we can say that this will remain the same. So okay, so we can run this. So the probability of first stage usage, 1/3 of the cases will be reused, and then it will increase. So in the first year, how many missions do we have? So let's copy. So from these numbers, we are copying the numbers here, because this will be a launch number, launch cadence. So now we have to think about that possibility of reusing first stages. It will be 0. So 33%, no way. It will explode, or even if it lands, then it will be somehow damaged, or we have to take it to pieces to see that what is happening here. So usually first stages which were landing in the early days, they were not launching them again, or if they were launching them, they were expandable, so they were not recovering it again, because they learned a lot and they developed a lot in the vehicles. So this is how they moved from block 3 to block 4, and then block 5, which was the final version of the rocket. So at the first times, we have to manufacture everything from scratch. Then we can possibility reusable first stages. So now we will have such vehicles, and or number of vehicles to be built will decreasing, but still, since half of the vehicles go kaboom, then we have to manufacture a lot. But after that, we are in the golden part of manufacturing because manufacturing numbers are dropping while their orders are still really high. So this is when we will make money. So from financial point of view and from economist point of view, that will be the third problem. We have to survive until we are reaching reliability at the engine. This is where ArianeSpace defaulted, and this is where also Virgin Orbit defaulted. Galactic, one of them defaulted. So because they were able to not survive the first problems with the launches. So that was Astra's Rocket 3. They had a really simple name for that one. It was a small sat launcher, so it was a small vehicle. But the problem was that from 9 launches, and long explosion at the pad because they started to move sideways instead of upwards. They had only 2 successes. So practically the money was running, the company was running out of money. So, which was sad. And still they are trying to keep themselves operational. Yeah, so they, yeah. So practically they defaulted in the last November on the financing, and practically they try to buy back the shares from the stock market. So that's such a price. And practically they were able to collect some money. Yeah. So unfortunately, co-founders had to buy this company back, which is sad because they went public just 3 years ago. So yeah. Nowadays they are trying to diversify, so they are much more like into satellite component manufacturing, not in the launch business. Launch business is quite narrow, and as you can see, it can have problems. So we are economists, so let's start to focus on number of sold